By Adam Cassano, Drew University.
Hello. I just wanted to say first, thank you for the invitation to come and speak to this group. It's a real honor. And I am going to be telling a story of my research today, and in some ways the path I took in getting it. And the main theme of this path is going to be, if you find something interesting and you have a passion for it, then you need to try and pursue it, because that is going to lead to the most professional fulfillment that you're going to have. And if others disagree with you, but you know it's what you are interested in, then you should follow it. Because, yes?
I have a quick introduction first before you start.
Oh, I'm sorry. I thought that was it when it was, please do, sorry.
There are more people watching on YouTube Live, so we'll get started now. Okay. First off, welcome everyone to the second day of the International Youth Brainstem Summit. Since I couldn't be at the opening ceremony, I would first like to extend my appreciation for our sponsors, the New York Academy of Sciences, Texas Instruments, the Art of Problem Solving, Sticker Mule, and the STEM Advocacy Institute. Secondly, thank you all for attending today. Today is the big day everyone has been waiting for, where you'll be presenting the projects you've all been working on so hard for the past few days. Additionally, thanks to our entire almost 40-person judging team and my fellow organizers of this event, who worked tirelessly behind the scenes to make this all happen. What excites you in science? Is it the prospect of discovering novel information about yourselves and your surroundings? Is it the ability to make a tangible, positive impact on people's lives? Or do you just enjoy the pure scientific process of making and testing hypotheses? Well, Dr. Adam Cassano will inspire you to do all of that and more. Dr. Cassano is an associate professor and chair of the chemistry department at Drew University in Madison, New Jersey. Prior to his time at Drew, he earned his bachelor's and doctoral degrees from Case Western Reserve University in Cleveland, Ohio. Over his professional career, he has developed passions for understanding the mechanisms of catalysis by enzymes and teaching the principles of chemistry to the next generations of scientists and citizens. At Drew, he has taught over a dozen different courses while specializing in biochemistry. And in his research, he is particularly interested in the role metal ions play in catalyzing the cleavage of phosphodiester bonds, a reaction critical to numerous biological processes. Even on top of that, he's the director of the New Jersey Governor's School, through which I met Dr. Cassano. Now that you know a bit more about him, I'll let him take the floor and introduce you both to his career and give you inspiration about how to pursue science.
Thank you, Ervin, for that very kind introduction and for the honor of inviting me to give this presentation. As Ervin said, I'm passionate about understanding enzyme catalysis and teaching chemistry to undergrads, and I'm going to tell you a little bit about of a story of how that happened in this talk. And so the title of the talk is Modeling Enzyme Catalysis via Metal Catalyzed Phosphodiester Hydrolysis, which doesn't sound very much like neuroscience, but because phosphodiesters are so important biologically, it turns out this is something that actually still does touch on neuroscience. And I'll be sure to explain that when it comes up in just a little bit. I'll start off by talking about what a phosphodiester is, because I have a nice image of it here. So a phosphoester bond is anything that has a phosphorus double bonded to an oxygen atom, and then having a connection where it connects to another oxygen atom, and then has an R group. This will be a carbon group, but everything else can be variable there. And because phosphate has three possible connections for these, we can have either a phosphomonoester, where we only have the one R connection, phosphodiesters, where we have two, and phosphotriesters, where we have three. One of the things that's very interesting about phosphodiesters is, even though it's kind of intermediate with the interactions, kinetically, it's the most stable, which means it hangs around for the longest period of time of all of these. As a result, these phosphodiester bonds are really useful in biology. They connect our genetic material, such as DNA, because they're very stable, and that's not something that we want to be breaking down. They're also very useful as signaling molecules, which I'll explain a little bit further why their chemistry makes them really good for signaling molecules coming up. So that's phosphodiester's. And so we'll talk more about those soon, but I wanted to start off with how I got hooked. Where did my passion, where did my excitement, was another word that Erevin used, for enzyme catalysis come from? And it came sort of very early on in my undergraduate career when I got to see just how amazing enzymes are as catalysts. And so this is basically just a bunch of different enzymes that have been studied, and it's a small subset. Their rate constant, or measure of how fast these reactions can happen in aqueous solution, and then that rate constant for the same chemical reaction happening in an enzyme active site. And you can see that even the wimpiest of these rate enhancements, bicarbonic anhydrase, is actually quite close to 10 million fold in catalysis. And the reason why that's so small actually is that this is all, this is already an extremely or a reasonably fast reaction in aqueous solution, and it's going at the order of a million times per second in an enzyme active site. I'm going to bring you up to this PDE6. This is phosphodiesterase 6, which is a phosphodiesterase that's actually involved in phototransduction of sending signals from our eyes when we catch light to our brain. So there's our neuroscience connection that's coming in here. And an estimate of the aqueous, and we can only use estimate because it's so slow, is about 3 times 10 to the negative 14th per second. So, and in the enzyme active site, we're up to 5,600, which is 2 times 10 to the 17th fold rate enhancement. And that's tough to wrap our heads around a little bit as anything other than, you know, a whole bunch of zeros coming out. So to put it in a little bit more context, this rate constant of 3 times 10 to the negative 14th comes out to a half-life approaching 1 million years. So it takes 1 million years for half of the compounds, which is cyclic GMP, to get hydrolyzed. In the enzyme active site, this rate constant corresponds to a half-life of about 1/10,000th of a second, so less than a millisecond. So from almost 1 million years to under a millisecond, that is what catalytic power of 1.9 times 10 to the 17th comes to. And I would say when I learned about this kind of information, I was like, I got to understand how that happens. And I don't care what anyone else says, this is the most interesting question in science. And it was for me, and it still is for me. I would say additionally, that the other thing that's fascinating about enzymes is that they are specific. You'll see that we have, 1.9 times 10 to the 17th, 5.6 times 10 to the 14th, 1.4 times 10 to the 17th. What's really amazing about them is that they're only catalyzing a specific reaction or a very small subset of reactions. Orotic acid monophosphate decarboxylase is not going to catalyze cyclic GMP hydrolysis. And phosphodiesterase 6 is not going to catalyze the decarboxylation of orotic acid monophosphate. So, so how they can do that really became a real interest in me. So then the next question would probably be, why phosphodiester's? And so this kind of takes me into graduate school. And basically, phosphodiester's are pretty cool in both biology and chemistry. Because they hold our genetic material together, phosphodiesterase, that hydrolysis is actually important in DNA replication. If an error is made, then it has to be hydrolyzed, and we can't be waiting 10 million years for that to happen. And so there are numerous nucleases involved with making corrections in DNA replication, in processing of our RNA, and also in cell signaling, as I said, including phototransduction. It's also super interesting chemically because of this rate enhancements that we've seen. It's among the biggest rate enhancements we see in enzymes. And it's catalyzed by both protein, which is what the majority of enzymes are made of, but also RNA, which nowadays we understand that RNA has numerous functions in the cell, but it used to be that was thought mostly to be maybe a little bit structural and some information, and we didn't realize it also played so many functions. And so the discovery of RNA enzymes kind of started us on this path of learning all the different things RNA is involved in. In the lab I worked in for my graduate work was trying to study the mechanisms of some of these catalytic RNAs, the way we might study how a protein enzyme catalyzes them. So that's why I got into phosphodiester hydrolysis and the enzymes that catalyze phosphodiester hydrolysis. So how do enzymes achieve catalysis? In some ways, the answer is disappointingly simple, but as with all things, we can say that the devil is in the details. So first we have to understand how a chemical reaction happens. And if this is basic for you, I apologize, but I'm trying to get us all to the same original piece. And so basically we can imagine our reactants, which is our phosphodiester and a hydroxide anion right here, having a certain structure. And for a phosphate, it tends to be tetrahedral. This is my attempt at a tetrahedron. And then what's going to happen is, as this hydroxide and this phosphodiester come close together, there's going to be some changes in structure that happen that actually require an increase in energy. So that means that these guys must be flying around with enough kinetic energy that they can come together and reach this maximally unfavorable structure that we call the transition state. And you'll notice it's not quite the same structure. This tetrahedron of the phosphodiester has kind of become more of a trigonal bipyramid, right? We can have a triangle across the equator, and there's a couple pyramids, one pointing up and one pointing down. And this turns out to be, this minimal, this maximally unstable structure, so that once we go and achieve it, we just get to almost like sliding down a slide of energy, come and form the products. And the products are lower in energy than reactants. So even though these reactions are super slow, thermodynamically, they're very favorable. And this is why phosphodiester's are really good for signals, because the signal can hang around for a long time until we have an enzyme that breaks down our signaling molecule, and then that enzyme can break it down very quickly to the products, and we don't have to worry about the products coming back and reforming the reactants until we want them to. All right. So how do we make the reaction go faster? Well, all we have to do really is lower this energy barrier. If we make the difference in energy between the reactants in the transition state smaller, then more molecules have enough energy to achieve the transition state. More molecules will achieve that transition state per unit of time, and the reaction will proceed faster. And there's actually a nice equation that we have for this, that the rate constant in the aqueous solution divided by the Kcat is going to be equal to e to the negative change in free energy of activation. So this from the reactant to the transition state, we call it the free energy of activation. And we can see that there is a difference in them. And so this delta delta G in that equation is referring to the difference between these two lines. For something like phosphodiesterase 6, where we had that 10 to the 1.9 times 10 to the 17th fold difference, that's about 99 kilojoules per mole. Putting this in the perspective of intermolecular forces, that's about somewhere in the neighborhood of 7 to 10 hydrogen bonds. And the key here is that this transition state structure is different than this reactant structure. And by the way, this product structure, if the enzyme can interact specifically with just the transition state or optimally for the transition state, then that means it's going to be easier for that transition state to be reached, and the reaction will move forward faster. Now, one of the things that you can see, the phosphodiester is negatively charged. The hydroxide that's attacking it is negatively charged. This leaving group that we call that's going to get kicked out is going to get an increasingly negative charge on it. What we really have here in this phosphodiester transition state is a lot of negative charges kind of close together. And this is why phosphodiesters are so slow, because it's very difficult to get all of these negative charges together in order to kick out that leaving group. So one very obvious way that an enzyme could stabilize this transition state is by placing some positive charges around it. And that's exactly what a bunch of different enzymes do. And there's lots of different ways that we could do that. An enzyme, and most often what we see is that they are what we call divalent, or they have two positive charges. So this would be things like magnesium 2+, calcium 2+, zinc 2+, manganese 2+. Those are probably the most common biological ones that we run into. One way that it could do is that the metal ion can interact with both the phosphodiester and that hydroxide nucleophile, bringing the nucleophile into a place where it can come in and make the attack. Alternatively, it could interact with the leaving group such that when the hydroxide attack, the buildup of negative charge on this leaving group is stabilized by the metal ion. You could imagine that we might have two metal ions, one on the nucleophile and one on the leaving group, the part thing that's going away. And so nucleophile is maybe a new word for some of you. It's just as it sounds. A nucleophile is something that loves the nucleus. And so they are often negatively charged, but always have a nice free pair of electrons to come in and form a new bond. But when that new bond forms, we're going to have to bust off another bond. And that's what the leaving group is, the part that's leaving. Another thing we could do if we had two metals is we could imagine two metals sort of both trying to activate the leaving group. So these are called Lewis acid mechanisms because the positive charge is interacting directly with these negative, with these electron groups. General acid-base alternatives involve the movement of protons. So it could be that instead of the hydroxide directly attacking, it could actually act to remove a proton. These hydroxides can act as bases, and it can remove a proton from a water molecule that's doing the actual attacking. It's a subtle difference, but an important one. Alternatively, on the leaving group, you could have a water molecule that's coordinated to this metal ion, and the metal ion can be helping that water molecule to donate a proton to that leaving group attacking it. And we see these all over the place in various ones. So Bies and Stites, way back in the early 90s, determined by a crystal structure that the 3' 5' exonuclease activity of DNA polymerase uses this method where there's one metal ion stabilizing the leaving group and another metal ion activating the nucleophile to make that happen. Phosphodiesterase 4, which has a lot of evolutionary relationship to phosphodiesterase 6, has this one where 2 metal ions are interacting with the nucleophile, both of them activating the nucleophile for attack. And then a different part of the enzyme is activating the leaving group. EcoR5, which is a restriction enzyme, has a situation where it has a water molecule coordinated to a metal ion, providing a hydrogen bond donor to that leaving group. And I keep accidentally clicking my mouse, I apologize. But it actually has a second metal ion that's acting in this direction where it's activating the nucleophile. So these are all various mechanisms of metal ions that are used by enzymes, but of course they're not the only thing that's used by enzymes. The enzymes have lots of other pieces to their active sites to help catalyze these reactions to get these amazing possibilities. So I'm going to get into this slide in a bit. One quick aside here is now we're going to vary a little bit from where I was working on my thinking about graduate career and catalytic RNA to where I am now at Drew University. And that happened because as I was a grad student, I had the opportunity to teach a biology lab, and I took advantage of that. And I found that every week, as much as my research was interesting to me and I enjoyed doing it and thinking about it, the fastest 3 hours of my week, every week, was those 3 hours I spent teaching lab. It just felt like I blinked and it was gone. And even though I was doing it extra outside of my long research hours, it was never a burden. I was always looking forward to it. I always felt energized after it. And I thought, maybe my brain is trying to tell me something here that I really enjoy teaching and working with students and going in that direction. And I tried teaching a full class in biochemistry at a local college, and I liked that just as much. And so I realized that when I graduated, I didn't want to give up research, but I wanted to make sure that teaching was going to be a big part of my job. And so I applied to Drew University, which is an institution where I would be working mostly with teaching undergraduates, still doing research, but that research would be about teaching undergraduates how to do research. And it was absolutely the right choice. I look forward to going to work every single day, and I get to meet a brilliant young minds every year. And so even though when I first said that to some of my mentors when I was in graduate school, they looked at me kind of funny. They said, well, you could probably have a really good career in research. And I said, yeah, but I really love teaching. And it was definitely the right choice for me. Now, the one thing about working at Drew is that it's not always easy to have the same kind of budgets. And it turned out that my interests and the questions that I wanted to ask might be a little bit more suited actually to a place like Drew. Because one thing that we can think about is that enzymes are big and complicated. So we can think about all of these possibilities and we might imagine, okay, what happens if we just remove this metal ion? If we want to know how much a metal ion is contributing to a reaction, we could imagine removing that metal ion and seeing what happens. But enzymes are big and complicated. This is phosphodiesterase 4, and there's its product hanging out there, really tiny in there. And if you look closely, there's a couple of metal ions involved. And you can't just remove or replace a metal ion and assume that you aren't only changing that part of the active site, because these metal ions are often important for holding the entire structure of the active site together. And so you can't really differentiate between the catalytic effect of that metal ion and the structural effect of that metal ion. So if you start trying to play with these metal ion binding sites and removing them, what I like to say is that you are getting a ceiling for what that effect could be. And oftentimes you completely kill activity of the enzyme. So so I said, you know what? Let's get a different number than the ceiling. Let's get the basement, right? What's the minimum possible effect that these metal ions could have? And that minimal effect that these ions can have is going to be the effect that they have in aqueous solution. Right. So I started working on a system that would allow us to look at this in aqueous solution and figure out what is the catalytic effect of a metal ion in the absence of an enzyme, because presumably the enzyme is not going to make the metal ion be worse. It might make it better, but at the very least, you would expect that the metal ion would be able to do in an enzyme active site what it was able to do in aqueous solution. So I started off with a system. It was a DNA model. Basically, the T in DNA stands for thymidine, and that's what is going on here. But instead of adding another nucleotide, I have this group here, which is referred to as paranitrophenol. And basically, the phenol comes from this aromatic ring and this oxygen. There's a nitro group on the opposite side, which we refer to in chemistry as being para. And this has two really useful things. Number one, this leaving group is much more active. It's much easier to kick off this bond than it is to kick off a different nucleotide. And that's important because obviously, as we said, this reaction is really, really slow with DNA. This helps speed it up enough that we can do it reasonably in the lab, although if we don't, we're often running reactions overnight and monitoring them, or sometimes even multiple days. The other thing that's really great about it is when it does get kicked off under alkaline pH conditions, it forms a compound paranitrophenolate that absorbs light, and it absorbs light at 400 nanometers, and so it is a yellow color. And so that allows us to monitor the reaction with the spectrophotometer, which is very easy. So basically the way we look at these reactions is we just measure that absorbance of paranitrophenol over time. This is in a reaction mixture with 0.3 molar calcium chloride. And you can see that as we go from low pH, low in quotations of 9.78 to a higher pH of 10.73, that rate of accumulating absorbance gets higher and higher. All right, so the rate of this reaction is going to be equal to a rate constant that we'll call KOH because it's for attack by the hydroxide, times the concentration of hydroxide and times the concentration of T5PNP. This thymidine, and sorry, T5-PNP is this thymidine 5' paranitrophenyl phosphate. It's way easier to say T5-PNP. So T5-PNP, if we keep that concentration consistent across all of our trials, the rate of this reaction should have a linear slope with hydroxide. And when I plot these slopes and for the rate of the reaction versus my concentration of hydroxide according to that pH, I do in fact get a nice straight line. And in this case, the slope was 0.172. And if I divide that by the concentration of my T5-PNP, I actually get this KOH, this rate constant for hydroxide. So I could go and I could compare what that second order rate constant was when I had no metal, when I had 0.3 molar calcium chloride, and when I had 0.3 molar magnesium chloride. And you can see that in either of the metals, it's a bit faster, 650-fold for calcium chloride and 800-fold for magnesium chloride. And so that's a good start in terms of thinking, okay, we get catalysis observable in aqueous solution, we can analyze what's going on. But immediately there is actually a little bit of a question going on here. Because magnesium is actually a much stronger Lewis acid than calcium is. And that was a little bit confusing. If you look at the effect on the acidity of water, it's about a 20-fold better Lewis acid. And so you would expect, you know, a much better, or much bigger catalytic effect from magnesium than from calcium. And so this was curious. And this wasn't where I was planning on going when I started, but as soon as I saw it, I said, we got to understand what's going on here. This could be interesting. So we started investigating what the mechanisms of these could be by first looking at how the concentration of the ion affected. And how the concentration of the ion affects this second order rate constant can give us information. So if you look at this guy, you might say, well, it looks kind of like a straight line. And if that was the case, what we would say is that what happens is that the magnesium ion interacts with the hydroxide. And that hydroxide can attack, but now instead of being negatively charged, net, when you consider the magnesium with it, it's actually kind of could be considered a positive charge. And so that may allow for the T5-PNP to come closer and to get attack. And we would end up with our products. And so KOH would be equal to this rate constant KMG, right? Which would be the rate constant catalyzed by magnesium times the magnesium concentration. So it'd just be a nice straight line. And it's not a bad fit. R squares of 0.98, most people will tell you, make you feel not so bad. But at the same time, it also looked a little bit like, well, we're overshooting down low and up here, we're undershooting in the middle. Maybe there's another model that actually works even better. And so that model would be, rather than the magnesium first interacting with hydroxide, the magnesium actually interacting with the phosphodiester to form a complex. And then actually it would be the hydroxide coming in and attacking that complex that comes through to form the products. And when you work out the algebra for this, you get an equation that is called a rectangular hyperbola, which is that if you look at these guys together, as the magnesium concentration gets very large, the magnesium will actually cancel out and you'll get a constant value. We call that saturation. It's basically, the idea is if we put enough magnesium in there, we can guarantee that all of our T5-PNP is bound to magnesium. And at that point, it doesn't matter how much more magnesium we add, we're not gonna get it. So it actually curves over and eventually will stop increasing at all. And it turned out that this equation fit our data much better with an R² of 0.995. And so we took that to think that the simplified scheme was that what we had was the magnesium ion interacting with the T5-PMP, and then the hydroxide attacking to give us products. And we were able to get a value for both the maximum rate constant if our T5-PMP were in fact completely bound by magnesium, and also a measure of the binding affinity for the magnesium. So that's cool. Now we can do the same thing with calcium. And I think in the interest of time, I'll quickly go through some things here. So we were able to eliminate the ones that had 2 metal ions, because you'll notice that my coefficient here is magnesium to the 1. So that means there's only 1 magnesium involved. But there's all these other ways that the magnesium could conceivably be involved. So we did a few tests. One was we went to see if magnesium could catalyze the reaction with a nucleophile other than water. And so we used this thing called 2-chloroquinoline. Basically, it's got a pair of electrons on this nitrogen, that if this pair of electrons interacts with the metal ion, there's no pair of electrons left to attack. Whereas if the metal ion is interacting with the phosphodiester and activating the leaving group, then the quinculadine should still be able to come in and attack. And what we saw was that when we had hydroxide, although we saw this great catalysis with the 3-chloroquinoline, we saw essentially the same rate. So that means we could eliminate all of the mechanisms where it was interacting with the leaving group. Now, was it directly interacting with the hydroxide, or was it acting as a general base? We used something called solvent deuterium isotope effects. And basically, that's the idea that if we replace this hydrogen with the deuterium, if it has to get transferred to the hydroxide, it turns out that that extra mass of the deuterium causes the reaction to be slower. So our K with hydrogen there divided by the K, the rate constant with deuterium, would have to be at least 1.5 fold greater. If, on the other hand, we didn't see a big effect, that would indicate that the magnesium was interacting directly. So we did this reaction. We looked at these K observed, these rate constants in both water and deuterium oxide, and we found that RK was somewhere in the neighborhood of 0.5. So that was substantially lower than 1, and may also be revealing a bit of an effect on the equilibrium isotope for the removal of the proton completely. But the bottom line is we were able to eliminate this general base mechanism. And so now we actually had a full mechanism for how magnesium was coming through and catalyzing. The magnesium comes in, water molecule gets replaced, and now we have our magnesium complex interacting with our T5-PMP. Hydroxide is then actually very quickly going to deprotonate that hydroxide in the magnesium, and then that hydroxide attached to the magnesium is going to come in and attack our phosphoryl to get our reaction. All right. So now we know what's happening in magnesium, what's going on with calcium. All right, so here's what magnesium looks like, to remind you, right? It increases, but the relative increase with each additional magnesium ion is getting less and less. If we look at calcium, particularly at the bottom, we see a difference that at the beginning, as we add calcium, the rate increase is actually going up and up, but then it starts to flatten out there. So it's telling us very quickly that there is in fact something different going on in the mechanism of calcium catalysis relative to magnesium catalysis. And this might help start explaining why calcium is a bit better than we were expecting. So there's a bunch of different possible mechanisms. Again, you've seen this one already. It just involves a single calcium. This was the same initial test that we did with magnesium. It gives a straight line. If it's going to be quadratic, curve up a little bit, it's possible that what we have is the possibility that calcium can either act by itself with one calcium, or maybe two calciums come together and then they are activating it together to give us products. On the other hand, it's possible that we could get pre-association with the T5PMP, right? Again, these are both showing the calcium interacting with the hydroxide first. If it interacts with the T5PMP first, what's going to end up happening is that we're going to get, again, that saturation. And what the saturation does is it's going to cause it to level out again. Now we could imagine the question is then, can it only operate through having two metal ions bound to it, or can it operate either with calcium, one calcium or two calciums? So these are all different models, and we actually tried a few others that we're going to try to use to explain what this behavior was. I'm going to show you all of them at once because it's another tale. Man, they all look kind of good, don't they? They're all showing something really close, especially here at the top. So what we did is we zoom in here at the bottom, we can actually start to see some differences in how they look. And what we see is that the line and the quadratic and the one for scheme 2, when we had pre-association but only one ion worked, they all don't do a good job of describing this data down below. However, that idea for scheme 1, where, just as a reminder, where you could have either calcium interact with T5PMP and then have the hydroxide attack, or you could have calcium dimerize kind of into some kind of complex with two calciums and then bind to the T5PMP and then have the hydroxide attack. So I call this the dual channel mechanism. That was the one that worked best. And by fitting it to the equation, and this big, long, nasty equation is basically what ends up happening when we try to convert this mechanism into a rate law, that we see that there is an opportunity for calcium to act in a first order, one calcium, or in a second order, two calciums way, and that they have two different rate constants, whether it's two calciums or one calcium, and different K apparents. We did the exact same experiments, or close to the exact same experiments that we did for the magnesium, and the short answer is it activating? Is there any activation of the leaving group? No, not for high calcium or low calcium. And the point about high calcium and low calcium is that low calcium, we're going to have our single calcium mechanism be more prevalent. And at high calcium, we're going to have the two calcium ion model be more prevalent. Is there general base catalysis? No, we don't see any isotope effects bigger than 1.2. So this actually then gives us a final model where magnesium is activating that hydroxide to come in and attack a single magnesium. With calcium, we can either have one, or we can also have this alternative model where two calciums come together and allow for attack. And this also then helps us explain our observation from the beginning, where calcium was able to work almost as well as magnesium in a way that was surprising. And that is basically that the single magnesium ion provides about 20 kilojoules per mole. The single calcium ion provides about 12 kilojoules per mole. And that's much more in line with the relative Lewis acidities of those two. But calcium has this additional channel of catalysis where two calciums can help stabilize that transition state through activating the nucleophile. And that leads to a level of stabilization that's close to the magnesium. So it's kind of, why did we see calcium work almost as well? It's because two calciums are about as good as one magnesium. And thinking back to phosphodiesterase 6 and phosphodiesterase 4, where there are two metal ions activating that nucleophile, we have a basement of somewhere, if we want to think about it as two calciums, that's actually not calcium in that enzyme. It tends to be magnesiums and zincs. So maybe if we think that a second magnesium ion would add again half as much, maybe we're talking about 30 kilojoules per mole. Not nearly 100 kilojoules per mole, but it's actually a pretty sizable chunk. And again, as I said, the enzyme active sites can improve this operation of these metal ions. And they also have lots of other pieces that they're doing. But this gives us sort of a basement or a range, a way to think about how much of that catalytic power is being contributed by these metal ions. And so I'm going to actually, I had a whole other story in my head about calcium catalyzing RNA cleavage that I think would take too long to go through in detail. The one thing I will point out that's kind of cool about it is that this is calcium catalyzing the RNA cleavage reaction. And what we see is there's only one calcium involved. Whereas for the T5PMP, we had that dual change. So it's very different calcium catalyzing RNA than it is calcium catalyzing T5PMP. And as a result, that transition state stabilization is again closer a little bit to that 12 kilojoules per mole. And I would like to make some acknowledgements to the students who did the work, which for what I spent most of my time presenting was Corey Cusack, Eric Lager, Evan Rockless, Brittany Kirk, Dylan Fagenbaum, and Steven Silva. Calcium RNA kinetics were done by Kyle Messina, Saif Yassin, and actually also Arlene Tarazona. And we didn't get to Julie's work on the cyclic AMP. If you have questions about that, I could talk about it a little bit, but I wanted to make sure there was some time open for more general questions. And then the last important acknowledgement to make is that all of these students and thus this work were supported by Drew University through grants to Drew University from the Howard Hughes Medical Institute, Bristol Myers Squibb, and Novartis. So with that, I would love to answer questions. And Aravind, should I keep sharing or should I stop sharing? What would be the best way to do this?
I think you can keep sharing in case someone has any specific questions.
All right,
Yeah, anyone, if you have questions, you can type them in the chat, or you can unmute yourself and say them verbally. I know that someone was typing questions in the chat before. I think that was Ahmad. If you want to ask your question verbally, you can do that. Or does anyone else have any questions meanwhile?
If Ahmad can't unmute his mic, you can probably ask a question for him.
Yeah, I'll ask his question. So let me go back.
Wait, no, I'm sorry. I just have to get my headset. So, with the catalyzation of everything and stuff, how exactly can we use this in a medical terminology?
oh, that's a great question. So,
Because
Yep.
I was making some of my own theories, and it seems like we can manually catalyze these things, and by manually catalyzing and focusing on DNA, it seems like we can alter specific parts of body with catalyzation.
So there's people doing that, and you may have heard of CRISPR-Cas9, and so that's using a biological term to do that. So people have looked at how can we make organometallic enzyme mimics that we might be able to give as a small molecule drug to do some things. You probably can't do the site-specific cleavage with that, but people have looked at possibly trying to combine some of these organometallic metal ion combinations that could maybe cleave RNA, and maybe you could cleave a specific RNA of a retrovirus or something like that. People have looked into those things. But you don't necessarily have to get that complicated. So another enzyme that uses this 2-metal ion mechanism, where you have one activating the nucleophile and one coordinating to the leaving group activating the nucleophile, is HIV integrase. And some of the newest generation HIV medications are actually integrase inhibitors. And if you look at the crystal structure of these integrase inhibitors, they are actually taking advantage of making contacts with these positively charged metal ions that are in the active site to help them bind and stick to that active site and act as an inhibitor. So understanding how and how much these metal ions play a role does provide some kind of information when thinking about how we might want to attack these. And with enzymes, maybe not phosphodiesterase 6, but certainly phosphodiesterase 4 is involved in signaling processes in the immune system and the inflammatory response. And so phosphodiesterase 4 inhibitors are often used as anti-inflammatories, like some of the eczema topical creams that are coming out have phosphodiesterase 4 inhibitors in them to stop that overreaction of the immune system there. So because phosphodiester cleavage is super important in biology, it turns out that there's a whole bunch of enzyme targets that use these metal ions, and understanding how they work can help inform when thinking about drug design.
Any other questions from the audience? You can type them in the chat, or you can unmute and say it verbally.
Another question. So, with the catalyzation, is there a certain limit that it reaches, or does it keep on going exponentially?
So I guess what you would imagine is the maximum would be, you know, coming down here. You know, you're ultimately, if you think about it, enzyme catalysis, you're going to be limited by how long it takes for the substrate to run into the enzyme. we're getting pretty close to it with this 1 times 10 to the 6th turnover number. Basically, the limiting factor for carbanic anhydrase is for the enzyme to actually make contact with its substrate. Now, if you could imagine that as, limiting with something like orotic acid monophosphate decarboxylase from 10 to the 6th to 10 to the -16th, we'd be talking about 10 to the 22nd. But I would say we're getting close to the upper bound for how fast the reaction can go, because that's roughly being now limited by diffusion happening. Bonds vibrate at the picosecond, I'm sorry, the femtosecond time scale. Some of the movements of enzymes that are important for catalysis can be down to the nanosecond time scale. So, this 10 to the 6th, we're getting pretty close to the limit in terms of for catalysis. But in terms of the fold catalysis, the rate enhancement, that's also going to depend on how fast the reaction is to start. And I'm happy to say anything general. Like I said, if you just want to understand what's going on with activation energies and transition states.
Yeah, so with activation, I remember last year my biology teacher kind of gave us a broken down version of basically what you're saying, and he basically said stuff like how different reactions react to different stuff, and how you basically can't have one reaction reacting to another thing. So that kind of confused me a bit.
So it sounds maybe like it's this idea of specificity. So I could actually very easily imagine how I can get 10 to the 17th rate enhancement for this reaction. I'll just throw it into the corona of the sun, which is, at millions of degrees Kelvin. Then yes, that reaction is going to go super fast. Actually, lots of reactions are going to go super fast. That reaction is just going to go bursting all over the place. So maybe we don't need to think about it being that hot. Maybe we want to just think about it being, in boiling water, or maybe even water under pressure so that it's boiling at a higher temperature. We can increase the temperature, and we can increase the rates of all of these reactions very simply. But if we only want to increase the reaction of one reaction in the cell, right, at a time, then we need to go back to lowering that activation energy for that one specific reaction, so that we don't go and catalyze all these other reactions at the same time. This also means that we can turn it on and off. When an enzyme is activated, it catalyzes the reaction, but then the enzyme can get turned off by other things in the cell, and it stops catalyzing the reaction if we don't want that reaction to happen.
Any other questions? You can even ask questions about Dr. Cassano's journey in science, or how you can get involved in research, anything like that, if you want to.
As a high school sophomore, how am I able to get involved in science and like STEM fields regarding this catalyzation of enzymes and stuff?
So I would say that lots of states are looking to bring research experiences to students at a younger and younger age. It used to be that you had to wait until graduate school to start doing research. And then there would maybe be a select few of undergraduates who would get to do research. Now, undergraduate research, everyone wants to be able to work with undergraduates and get started. and more now there's now some opportunities out there for high school students. I would look at opportunities that might be institutions near you, or there may be programs by your state or nation that is involved with trying to connect interested students with interested research mentors in order to be able to get them started working. And yes, if this went over people's heads a little bit today, one of the things is if you dive in and you are working on it and this is what you're thinking about for a summer, it will actually make way more sense, and things that you struggle with and you think you will never understand will become easy by the end of those 8 weeks. So I would look towards institutions directly, but also towards various programs supported or advertised by government.
Any other last questions? Anything in general or specific about Dr. Cassano's research?